All right, let's continue on with some of the problems we have from Chapter 7. So we're in looking at cost details. Homework for this chapter is due Monday, so plan on hitting that. The problems for Chapter 7. To foreshadow a bit, our next chapter coming up is going to be perfect competition. So then we'll be dropping into the market system under a competitive setting.
When is the test?
I haven't decided yet, but it'll be coming up pretty soon. We'll probably talk about it on Monday next week. Okay. Anything else? Let's see. We left off. We got through the whole problem, if I remember right. Correct. Instead of jumping to the, well, let's go ahead and jump to that little box. So the little box down at the bottom. Suppose that the long-run total cost function for a firm is that function, and its long-run marginal cost function is this. At what levels of output will the firm face economies of scale? Diseconomies of scale. Hint, these cost functions yield a typical U-shaped long-run average cost. All right, so something we hit in principles class. So part of this is dusting off the cobwebs, and part of it is taking an equation approach to things. So long run, what's the distinction for long run? All things are variable. So how do you see that in that equation? Look at that equation for long run cost. Tell me what you see that's different. There's no constant term. So each expression there is a function of Q, right? So that's kind of a little indicator from the equation that we're dealing with a long run. Okay, so what about economies of scale? What's going on with economies of scale? Does anybody remember that?
Well, over the long run, isn't it like 3 different?
There was a few different phases.
Costs, and then so those compared to each other, the economies of scale, depending on how large or small, how big it was, or something like that.
Not so much on the size of the company. The scale part of economies of scale dealt with quantity, yes. So as you increase the scale of production, which means going from 0 to something big, as we increase the scale of the production, in the long run, what was the key thing happening if you have economies of scale? Costs are going down. Long run average costs are falling. The total cost function is going up. That's an increasing function, right? If I want more stuff, I need more product. If we shove a Q into this, each time I put in a bigger Q, I get a higher number over here. So costs are always going up, but the average is going to be falling. So on our most general curve, the way this one would look, it says it gives you a hint that it's got the typical bowl-shaped, U-shaped curve. Conceptually, there could be a flat spot, maybe, where it just remains constant for a while. I mean, it could take on a number of different forms. The functional form would look different. But we've got long-run average total cost that kind of look like this. And the portion where there's economies of scale is this range, right to wherever that bottoming out spot is. This whole region, or this whole production range, is economies of scale. So long run average costs are falling over that production range. The more you produce, the lower your cost on average. So that's economies of scale. Then we just diss that, and we get the other case where there might become a point where We are having management constraints is often pointed to. We've got middle managers talking to managers. We can't quite be as efficient as we were at some level once we get to be super big maybe. So theoretically we can have diseconomies of scale. All right, so we've got a long run marginal cost curve of 22,600 minus 600Q plus 3Q squared. Calculus people, what is this in relationship to this? First derivative, so marginal cost is always the first derivative of the cost function. All right. So what's the first question asking here? At what levels of output will the firm face economies of scale? How do we take that information? Right. So this is kind of our whatever we want to call this. Let's just call it Q1. Wherever Q1 is kind of this break point.
Isn't that where they're
Okay, is it where they're equal?
No.
Where the average and the marginal are equal. Good. So we have not drawn the average. So in order to convert this to average, we need to divide by Q. So then we've got 22,600 minus 300Q plus Q squared. Okay. By dividing that top equation by Q, that gives us our long run average cost. And the properties of marginal and average are still the same. If we were to graph out the long run marginal cost, it's going to be lying below the average and then coming up. So conceptually with a graph, it looks like this. And go ahead and solve that. See what you get.
Are there going to be times where you get the long run average total cost? I'm just in terms of calculus right now. You're like trying to find where the derivative's equal to zero to find that point rather than
Yes.
there.
Yeah. So what's the derivative equal to on this function at this point?
It's equal to zero.
It's equal to 0.
That's what I was saying.
Yeah, so you'd set it equal to 0. But then you got some issues, some other tests that you have to do for the second order condition. If you have a circle function, that's got a derivative of 0, that's got a derivative of 0. So the second derivative has to be increasing rather than decreasing. There's another step that you have to take with testing what area of the function you're on.
Even on this.
Probably not with this one, although I'm not sure off the top of my head. I guess you can test it right now.
Whatever.
You can test it right now.
Do you want me to?
Yeah. Who's got an answer? Just doing it the good old algebra way. What'd you get? 150. That's right. So quantity equals 150. So all we're doing is set long run marginal cost equal to long run average total cost, and you get the quantity equals 50. Okay, any questions on that? Did you do your test?
It worked very quickly.
Yep. A little quicker. What's that?
Should.
Yeah. Yep, that's the calculus.
Because that's what I actually did for long run total cost.
Yeah, with any of these you can start, and I'll try to point out the calculus as we go through because it's not even that difficult really. If you're okay with calculus, it's not too bad in some cases. cranking this stuff out with first derivatives and second derivatives. Okay, good. Just one other thing to point out. How could you test whether you were right? How could you do some double checks to make sure 150? So you did the math, you came up with 150. If you didn't have Russ here to say, yep, that's the right answer, how could you test? Plug it in. Yeah, just plug and chug some numbers. Take 152 or 151 or 160, anything to the right here, plug it in, see what you get, right? Plug in 150, see what you get. Plug in something less, see what you get. If you did it right, then the cost should be a little higher at a lower number, and the cost should be a little higher to the right of that. So we've minimized the cost. Okay, any other last questions on that one? Yes?
If they were asking you, like it says, at what levels of output will the firm face economies of scale, would you include 150 in that, or is it all the values less than 150?
Actually.
Say that again. If
If they asked you at what quantities they were facing economies of scale, would you include the 150, or would it be all the values less than 150?
less than 150. Yeah, technically constant right at that moment. And that kind of brings up where you could possibly have a long run average cost curve that flattens out, and then it kind of goes up. So if you have a flat portion. So quantities where long run average cost is decreasing, the function is decreasing at all levels less than 150 from a technical standpoint. Yep.
I did some the other night on 17. It's kind of the same exact, not the same exact, but same concept. And I actually had it up to 150, like, well, it was up to 4. It was probably better. They included 150 as part of the economies of scale.
So they said less than or equal to?
Less than or equal, like.
I'm not going to ding you on the test for it. I guess if we're getting down to that technical, as long as you found 150. But so the one, if we go from a math standpoint, kind of like what John was thinking, at 150, is the function decreasing? No, at 150, it is completely constant and flat. So technically, right at that point, the function is no longer decreasing function. Because we solved, and in fact, that's exactly what we were solving for, was where it was completely flat, where the slope was flat. So first derivatives downward sloping, first derivatives upward sloping.
Conceptually,
But in real life, when we're talking about practical applications, it's 150, right? I mean, that's our break point, and kind of. But yes.
that's what I was saying. Like when you talk about the marginal cost curve, I was just thinking like that's why I was thinking maybe 150 would be included, because up until 150 you're still not.
Yeah, at 150, we always think about the next thing, right?
Yeah.
So what would be my next move? And you're right, then your costs go up at 151. So you're facing diseconomies of scale at 150. All right, next one. Flip over your page. Steve & Sons Solar Panels has a production function represented by Q equals 4KL, where the marginal product is 4K, the marginal product capital is 4L. The current wage is $8 an hour. The rental rate is 10. In the short run, the plant's capital stock is fixed at 10. What is the cost the firm faces if it wants to produce 200 solar panels? All right, first step comes to mind. What's the first step? What's kind of a missing link here? Okay, you got the cost function. Plug in 10 for capital, but then you're going to be missing something, which is really kind of your first step. but I like your approach. I would maybe lay out the cost function in its generic form. Kind of helps you see the problem.
Aren't you solving for the amount of labor that you're doing?
We got to solve for labor, yeah. So that's what's going to be the missing link here at 200. The production function tells us that amount. So we've got total cost in its generic form, wage times labor plus rental rate times capital. What do we got? $8 times labor plus, we know the rental rate of 10 times 10 units of capital. So right away it pops out that we're missing L. So we need to go to our production function where Q equals 4KL. We're told by the problem we need to have 200 units times 4 times 10 times L. So what do we get? Let you guys catch up. L equals, Brinson, how come you're on froze?
Huh?
How come you're froze?
Oh, it's just that.
Okay. I'll start writing. What'd you get for L? 5. Okay. So L equals 200 divided by 40 equals 5. Now we've got our answer up top. We can substitute in 8 times 5 plus 100, giving us $140 worth of cost. What will the firm wish to do in the long run to minimize costs of producing 200 solar panels? How much will the firm save? Hint, you may review chapter 6 to remember how a firm optimizes when labor and capital are both flexible. So what do we got to do?
They're putting out that it's in the long run, which means capital's flexible enough.
Okay, good.
Since your cost ratio, I mean, right now you're at 5 labor and 10 capital, which isn't necessarily the most efficient.
So you bringing up the question is, what is the cost efficient combo of labor and capital if quantity equals 200? Just to kind of restate what the question is asking, right? So what do we fall back on? What condition? Go ahead. Marginal rate of technical substitutions got to be equal to the price ratio, which is the input price ratio in this case. So we're falling back to isoquant of 200. There exists somewhere an isocost of some unknown amount potentially, but I know that in equilibrium, K star and L star, my optimal, which is what I'm asking for here, the cost efficient combo looks like that graphically. For the exam, whenever it is, you guys need to know right off the top of your head the condition that shows this graphically. Chelsea was hinting at it, and maybe we said the whole thing, but let's make sure we got that right off. You said the MRTS, what did you say that is again? The marginal rate of technical substitution of labor and capital has to be equal to the price ratio, which is the slope of the isocost line. So the the marginal rate of technical substitution is what? I'm going to hold off on the weight. I'm going to get there. But what is the, let's just take that in a piece. The marginal rate of technical substitution, which is the slope of the isoquant. Slope of isoquant, which is here. Marginal product, good. This is always the tricky dicky thing, right? Which one goes up top? Labor. Capital. Marginal product of labor over the marginal product of capital. In equilibrium, that happens, if I'm color coding this, maybe this would have been good if I would have did this in red, equals the slope of the red iso cost line, which is the, which one goes on top, the wage or the rental rate? The wage, which matches the same thing of whatever we're measuring down there over the rental rate. That is called the first order condition for cost minimization. So the big scheme of things that we learned from chapter 6 that now we're tying back to some cost here is how do I minimize cost subject to a given quantity? That was kind of the big problem. How do I minimize cost subject to a quantity restriction? So the optimization problem, which is kind of what we always want to think about on the big scheme of things when we start to get lost. Well, what am I talking about? Am I talking about consumer? Oh yeah, maximize utility subject to an income constraint. What if I'm doing it in terms of expenditure? Minimize expenditure subject to a given level of utility, right? That was the dual to the consumer problem. Now I've got a business mind on. Eventually we're going to get to maximizing profits, choosing an optimal quantity. Here we're looking at minimizing cost, minimize total cost subject to a quantity constraint. We're always falling back to this logic. What am I trying to make better subject to what constraint? The big problem of economics, trying to satisfy unlimited wants with limited resources. What am I trying to do? What's my constraint? What am I limited to? Right? So the problem is always set up similar to that. You also want to remind yourself of the choice variables. So I'm going to minimize total cost subject to a quantity constraint by choosing an optimal level of what in this case? An optimal quantity of labor and capital. Those are my choice variables. So minimize total cost subject to a quantity constraint by choosing L and K. My choice variables, the quantity of labor and the quantity of capital. All right, so back to this problem. Looks like we've got an 8 and a 10 here. So, anybody got some answers yet? Don't be surprised that some of these break down to something very simple. Sometimes that can almost seem like, oh, I must have did something wrong, right? When we start to see something break down fairly quickly to that. So yeah, start plugging in the numbers. So right now we've got, following our first order condition over there, we've got K over L equals 8 over 10. So where do you go from here? K is a function of L. Okay, good. So that's a good place to start. Find K as a function of L. You can find L as a function of K if you want it. You can take the problem wherever you kind of want to go with it. Once you find one as a function of another, what do you have to do? What did you do next? Into the production function, yes, into the quantity. So now take that K and substitute it into your production function, which was 4KL, but now we've got 4. K is 0.8L times L. So 3.2 L squared. Have to do a little square root action, solve for L. What'd you guys get? When I do these little squirrely things, it's kind of like I'm jumping a few steps that you might not want to jump yourself, but that's what these little curly Q things are. There might be a few steps in between jumping to the answer. I don't know who I borrowed that from. Some instructor or friend. Actually, I kind of remember it from Dan Fanuff. He is a professor up in Wisconsin now. He's at UNC, but I think he used to do the little curly Q thing. It's kind of like yada, yada, yada. But you guys need to know those yadas for the test, so you can't just curly Q your way down. Who's brave? What'd you get for L?
It's like a little bit less.
A little bit less than 8?
I don't know because my calculator doesn't.
Oh, you don't have your calculator. Okay. Oh, you don't have the square root?
I don't have it on this.
Oh, okay. So yeah, good point to bring up for the test. You're not using phones, right? That's not allowed in this class. So make sure you get a calculator that can do some of the square root functions and stuff, which isn't too big of a calculator, but some basic calculator at least. Who does have it? What did you have? A little under 8. I buy that. 7.91. 7.91. Okay, good. So L equals 7.91, and then K, bring this back up to this equation would be a simple way to do it. Solve for K. 7.91 times 0.8 means that K equals 6.33. So, back to part B. How much will the firm save? What will the firm wish to do in the long run to minimize cost? How much will the firm save? What do you need to do? Let's talk it through before we even jump into this. So we've got K equal to 6.33, L equal to 7.91. Okay, stop working, start talking. What do we do?
What do you? Oh, yeah.
Got my thing here. Guy, cameraman's a little off. So plug what into total cost? Using these numbers. And then do what? And the original, which we never calculated either, right? Oh, that's right. We did calculate. I'm sorry. You're right. Yeah. The difference from that from 140. That's right out there. First, that was the one I erased. All right. So once somebody gets an answer, tell me what you got for the new total cost. 129 point what? 0.66. Did everybody get that? We got 8 times 7.1 for the labor bill. The capital bill comes in at 10 times 6.33. Anybody get anything different? I had something a little bit different. 126.58. It's a little bit of rounding. Not sure where that all came from, but 126.58. Have we answered the question yet? No. What's the firm going to save? $13 and some change. All right, $13.42. So where did that ISO cost curve lie before? Back to this problem. We weren't at some optimal. Was it a higher slope or a flatter slope compared to the optimal? Higher? Now how do you know that? Maybe just by looking at the numbers. Decrease capital and increase labor would be one way to kind of at least eyeball what's going on. Because optimally we want to drop capital and increase labor. So we must have been at a point over here somewhere. And we could be less by making adjustments. Okay. Questions on that one? Okay, the remainder of the time today, we're going to start talking about perfect competition. So I think I'm trying to dust off a few cobwebs here of some concepts. Perfect competition, price taker or price maker? Price taker. What does that mean? Yes. So what the market's kicking out is what the market, or is what the firm is facing in terms of a price. Price of resources or price of output? Output. Okay, so I mentally and graphically come back to this picture for these problems. And when you go through some problems that only have equations and words, you might want to think back to this basic setup here. The market and the representative firm. You might be given a supply and demand equation from which you have to calculate market price and market quantity. So we'll put a little Q over here for the representative firm. One equation that pops out right away is the relationship between market supply and the individual firm supply. So big Q equals the sum of the little guys for I equals 1 to n firms. Farmer Joe, Farmer Ted, Farmer Dick, Farmer Harry, right? We're adding up all of the individual firms' quantities to get the market quantity. So, characteristics of perfect competition, kind of some of our baseline assumptions. One, large number of identical firms. I'm going to put a little bit more detail than what we did in principles class. I didn't say identical firms before, but that's essentially what we're doing. Unless you see something stated differently, what that means is we're assuming all firms have the same cost functions, right? They look the same, they taste the same, they all smell the same. So this is assumptions under perfect competition. That's your typical baseline assumption. Just pretend that they're identical firms. Those identical firms are producing a homogeneous product. We got identical firms producing identical products. You can't distinguish one farmer's corn from another farmer's corn. Last basic assumption is free entry and exit. People can start up a business, they can get out of the business. Basically seamlessly or cost-free. It's pretty much easy to get in and out. We can foreshadow a little bit now that we've been through principles class to remember what was the thing that happened because of free entry and exit. You remember some consequences that that condition led to? It was easy for firms to get in and out, and you can think back to profits. There's no economic profit, right? So free entry and exit caused the long run expectation, long run equilibrium, that there's zero economic profit. So free entry and exit gives zero economic profit in the long run. So, thinking back to earlier today, we had a long run average total cost curve. How could that be helpful to think about this condition? What did we do earlier today? We did the economies of scale, and what did we solve for? The quantity. That quantity was 150 in that example, right? So if we were given a bunch of firms and that all had if there was 20 firms that had the long run average cost function that looked like that, we could make a long run prediction of what big Q would be, right? Because of this condition, we know that that's where price is going to get to in the long run eventually. So there'd be 20 firms producing 150 units each under these conditions. So that's how we'll kind of use the information and go back and forth possibly from the market to the firm and backwards and forwards, kind of interweaving some of these predictions that we got out of principles class. But then it'll come down to solving equations and okay, let's find where that point is. It's 150 units and kind of roll from there. So the rest of this picture, the firm is a price taker. Whatever the market price is represents now the demand curve for Farmer Joe's corn. the demand curve being flat at the given market price meant that the revenue generated by each additional unit was also constant and equal to the market price. So demand equaled marginal revenue for the individual firm. The revenue generated by each additional bushel of corn was equal to the market price. Farmer Joe or any other average Joe can't get away from the law of diminishing marginal product and therefore faces an increasing marginal cost curve. The firm maximizes profits by producing the quantity where the revenue generated by the last unit is equal to the cost of the last unit. If we jump to long run, which we'll do some variations of movements of how we get there, but the long run average cost curve would be expected to be right there. And now you start to see some of the pieces coming together. We can solve for this quantity by putting marginal cost equal to average total cost. We could also solve for this quantity by taking a marginal revenue function, setting it equal to the marginal cost function at that point. So there's a number of different ways we could tackle the animal depending on the data, the information that's given to you in a problem. So know this graph, like hopefully you knew it before in principles class, but this is long run. This is what we expect the long run situation in perfect competition to be. Zero economic profit, price taker, and that's our setup. Burn that into your brains and that'll pay dividends as we get into equations a little bit later. All right, that's it for today.